Hi everybody. So this is a second version of lesson 2.1. So I've had three of you now bring up to me or start asking questions about this lesson and specifically how to perform the integrals. When I showed you it in the original lesson 2.1, a lot of what I did for the integral used both the power rule that we're going to talk about today and also just looking at it by inspection, seeing what, after using the power rule, then taking the derivative to solve and figure out what's missing. Instead, in this lesson, I'm going to teach you a second method. So it's the power rule in logarithmic form, but it's using substitution. Okay, so substitution was common when you looked at the chain rule. Okay. So in this lesson, I'm going to do the same problems that are in the other video for lesson 2.1, but I'm going to focus on doing them using a different method. Okay. So starting off with this, we look at the power rule. So the power rule is the integral of a function x to the n, whether it's x squared, like I have in the example here, or something else, is simply equal to the x to the exponent n plus 1, so adding 1 to the exponent, divided by that same n plus 1 term, plus a constant. So if we use that and we use the integral of x squared as an example, we get x to the exponent 2 plus 1 divided by that same exponent 2 plus 1 plus a constant, or 1/3 x cubed plus a constant. The reason for this number in the denominator is because, remember, every time you take an integral, you can always check whether your integral is correct by taking the corresponding derivative of it. So if we do that, and we take the derivative of 1/3 x cubed, okay, we get 1/3 times 3x to the 3 minus 1, which the 3's cancel, and we're left with x squared. So we know that it's correct because we get the same value that's sitting here in the integral. Now, this is a simple example with just one term, but what if you had an example like the one below here? That's the integral of sine inverse of x divided by the square root of 1 minus x squared. So we actually know that the derivative of sine inverse of x with respect to x is 1 over the square root of 1 minus x squared. So we see both the original term and the derivative. And usually when you see items like this, you can solve it by using the method of substitution. And it's similar to the chain rule. You select one of the variables to be your function u, okay? And then the remainder of it, you try and substitute in du for the remainder of this function here, which in this case, if I let u equal sine inverse of x, the derivative of it, okay, is 1 over the square root of 1 minus x squared, okay? I'm then going to substitute in a value for du, okay? So I'm going to look at this example. I know I had it on the other slide, but let's go at it from the start, and I'll show you how to use it, do it using substitution. So we start by looking at the function. This is the integral of sine inverse of x divided by the square root of 1 minus x squared. So it's usually either the sine function, or if you have something like 2x plus 3 cubed, it's usually whatever is in that bracket that you set to be the function u. Okay, that's usually the easiest way to do it. So in this case, I'm going to let u be sine inverse of x. Okay, so now I need to substitute in for the rest of this. The 1 over 1 minus x squared, the square root of, times dx. So I'm going to take the derivative of this. So we get du by dx, and the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. So you can see we're close, but what we need is that dx function. So you can consider this piece like a fraction. And you can actually move the dx to the other side by multiplying both sides by dx. Okay? So on the left-hand side, the dx's would cancel. And we have that du is equal to 1 over the square root of 1 minus x squared times dx. So now we have two different items that represent functions in here. So substitution's goal is to make your integral easier. So if I substitute in for u and for du, I get the integral of, instead of sine inverse, I'm going to plug in u, and instead of dx, or 1 over 1 minus x squared, the square root, times dx, I'm going to substitute in du, right, because it's equal to it. So I end up with just u times du. Now we just have a simple expression, just like the one we did with x squared. So we can use the power rule. Remember the power rule, the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus a constant. So we can do the same thing here. U is the same as u to the exponent 1. So the integral becomes u to the exponent 1 plus 1 divided by n plus 1. Remember, 1 plus 1. So the same value that's in this exponent here, plus a constant. So what we're left with is 1/2 u squared plus a constant. And our final step is to then substitute in our function for u, which is 1/2 sine inverse of x squared plus a constant. Again, you can always check whether or not your answer is correct by then taking the derivative. So if we took the derivative of this, we would get 1/2 times 2 sine inverse of x, and again, to the exponent 2 minus 1. And remember, because of the chain rule, we'd have to take the derivative of what's inside the brackets here, which is 1 over the square root of 1 minus x squared. So the 2's here would cancel, and you see that what we're going to be left with is sine inverse of x over the square root of 1 minus x squared. That's just to check your answer. Okay, that's the only reason you have to do that step. But using substitution as opposed to looking at it kind of by inspection is that it ends up with a much easier integral. So let's look at a few examples. Again, if you've already watched the other video, the other lesson 2.1, it's the same examples. I'm just doing them using a different method. So this is evaluating the integral of x cubed plus 3 squared times x squared dx. Again, anytime you see a function like this in the brackets raised to an exponent, that's usually a good function to let represent u. So I'm going to let u equal x cubed plus 3. Okay? So now I need to find du. So du by dx, in this case, is equal to 3x squared, because the derivative of the constant is just 0. So you can see we're close here. We have an x squared and a dx. So now to have dx on the one side of the equation, I'm going to multiply both sides by dx. So they'll cancel on the left side, and we're left with du is equal to 3x squared dx. So we're almost there, right? You see an x squared dx term here, but you don't see that 3 there, which means we have to move it to the other side. So if we divide both sides by 3, we get 1 over 3 times du is equal to x squared dx. So now we have two terms here that we can simply substitute in for. Okay? If I do that, then my integral becomes the integral of, instead of x cubed plus 3, it's u squared. And instead of x squared dx, it's 1 over 3 times du. So now before I take this integral, I always like to remove the constants. Okay, remember, the integral of a constant number, you can move the constant outside of the integral. So this becomes 1 over 3 times the integral of u squared du. Now remember, we can just use power rule for this, which means this becomes 1 over 3 times u to the 2 plus 1 divided by the same exponent, 2 plus 1, plus a constant. So if we simplify this, we have 1 over 3, and 2 plus 1 in this denominator is 3. So we have 1 over 3 times 1 over 3, which is 1 over 9, u cubed plus a constant. Our last step is then to substitute in our value for u. So we do that, we get 1 over 9 times x cubed plus 3 cubed plus a constant. Okay? So again, we arrive at the same answer, okay, except it's just looking at it in a different way. Okay, so our next example is using trigonometric functions. So let's evaluate the integral of 4 sine of 2x squared times cosine of 2x dx. Again, the function with the exponent is always the better bet to use as the function u. So I'm going to let u equal 4 sine of 2x. Okay? So du by dx is equal to 4 cosine of 2x. Again, remember, multiplied by the derivative of the function inside the trigonometric function. In this case, the derivative of 2x is simply 2. So du by dx is equal to 8 cosine of 2x. Solving to just have du, remember we want to remove that cosine function and the dx. Multiply both sides by dx. So the dx's on the left cancel, and we're left with du is equal to 8 cosine of 2x dx. Again, we're close here. We're not quite there because we have a cosine 2x and a dx, but we don't have an 8 there. So we have to move the 8 to the other side. So to do that, we divide both sides by 8, and we're left with 1 over 8 times du is equal to cosine 2x dx. So now we have our two expressions that we can simply substitute in. If we do that, we get the integral of, instead of 4 sine of 2x, it's u squared. And instead of cosine 2x dx, it's 1 over 8 times du. So now we have the integral of u, and it's du, so with respect to u. And we have this constant 1 over 8. So I'm going to move the constant outside of the integral again. So it equals 1 over 8 times the integral of u squared du. So using the power rule, we can take this integral, and we get 1 over 8 multiplied by u to the exponent, 2 plus 1, remember adding 1 using the power rule, divided by that same exponent, 2 plus 1, and this is plus a constant. Sorry, disregard what I was going to say. Simplifying this, we get 1 over 24 because we have 2 plus 1, which is 3 times 8, okay, multiplying fractions. And that becomes u cubed plus a constant. So substituting in our value for u, we get 1 over 24 times 4 sine of 2x cubed plus a constant. Okay? So this is very similar to using the chain rule, but just in the reverse. Okay, so let's look at a third example. This time the integral has bounds, okay, so a minimum and a maximum. Remember, for integrals, you're finding the area under a curve. So in this case, we're finding the integral from -1 to 0 of 1/4 x squared times 2x cubed plus 4 cubed dx. So from -1 to 0 means this is a graph of this function. So we're finding the integral, or the area under the curve, from -1 to 0. So all this portion here that I'm highlighting in red. So our final answer will come out to a number. Okay. So starting again, looking at this function, we have an item in the brackets raised to an exponent. That's always a good idea to start with as our function u, using substitution. So I'm going to let u equal 2x cubed plus 4. That's a terrible 4. So du by dx, remember we need to substitute in for the u and also removing the dx. So du by dx in this case is 6x squared because the derivative of that constant is simply 0. So solving for du, okay, multiplying both sides by du. They cancel on the left, and we get du is equal to 6x squared, dx. Okay, multiplying both sides by dx. Okay, we're close, right? We've got something to put into these brackets here, and we have an x squared and a dx, but we have a 6 here. Okay, so we need to remove that 6 because we can't substitute in for the 6 when it's not in this equation. Which means we have to divide both sides by 6. What we're left with is 1 over 6 times du is x squared dx. Okay? So now if I substitute all of these values into this integral, I get the integral from -1 to 0 of 1 over 4 times u cubed, okay, substituting in for the brackets, and then removing the x squared and the dx, instead I have 1 over 6 times du. So this can be written as the integral from -1 to 0, okay, of 1 over 24 u cubed du. So just like I've done in the past, I always like to remove the constants and put them outside of the integral. So this becomes 1 over 24 times the integral from -1 to 0 of u cubed du. So now using the power rule, okay, this is the same as 1 over 24 times u to the 3 plus 1 divided by that same exponent, 3 plus 1, okay, plus a constant. So if I simplify this, I have 1 over 24, and then I also have a 1 over 4, because 3 plus 1 here is 4. So multiplying those together, I get 1 over 96, u to the 4 plus a constant. So our last step is now substituting in the value for u, gives us 1 over 96 times 2x cubed plus 4 to the exponent 4 plus a constant. So now we have boundaries. So we're going to get to a final answer that's a number because we're going to evaluate it at both boundaries. So at 0 first, and then subtracting the value substituted at -1. So we end up with 1 over 96, and then 2 times 0 cubed plus 4 plus a constant. That's at x equals 0, minus 1 over 96 times 2 times -1 cubed plus 4 to the exponent 4 plus a constant. So you can see we have plus a constant and minus a constant because of the minus sign here. So they will always cancel in this scenario when we have bounds. So simplifying these, the first term, we have 1 over 96, and that is 2 times 0 cubed is just 0. So we're left with just 4 to the exponent 4, which is 256, minus, again, 1 over 96. And in brackets here, we have 2 times -1 cubed, which becomes -2, plus 4. So this simplifies to 2 to the exponent 4, which is 16. Okay, how to think about that one. So now they both have the same denominator, so we can simply subtract the numerators. That gives us 240 divided by 96, which if you put that in your calculator, gives you a nice even 2.5. Okay, so when you have bounds like this, you're always going to end up with a number as a solution. Okay. So this rule is great. Okay, the power rule is great for all instances except for when the value of n is -1. Okay, if it's -1, okay, let's say we have x to the -1, that's the same as 1 over x. Then if we use the power rule, we're going to have x to the -1 plus 1 divided by -1 plus 1. That's just following the same rule we have, which means we have x to the exponent 0 divided by 0. You can't have a number divided by 0. Okay, that gives you infinity. Remember when we talked about 0 over 0 and infinity over infinity and having to use L'Hopital's rule. Okay, so the same thing applies here. But the basic logarithmic form comes to the rescue. Okay, remember the derivative of the ln function, ln of a function u, is 1 over that same function u times the derivative of it. Okay, so if we have x to the -1, that's the same as 1 over x. So looking at this form, it's 1 over a function. So we have 1 over x. X is a function. So the integral of 1 over x is simply ln of x. Okay? So like I mentioned in the last slide, right, you can take this form, and if you have something to the exponent -1, you can simply make the integral being the ln of the function instead. The only caveat to that is ln is undefined when x is 0 or less than 0. So it has to be greater than 0, which means that this integral is the ln of the absolute value of that function. That's what these two lines, okay, represent, one on each side, is the absolute value, meaning that number is always going to be positive. All right? So let's look at a few examples using the logarithmic form. Okay, and I want to show you in this first one, if we try to do substitution, why it's not going to work. So evaluate the integral of 1 over x plus 4 dx. So we know if it's 1 over a function, okay, and the function doesn't have an exponent, it's just 1 over x plus 4. Based on what we saw in the last slide, the integral of this would simply be ln of x plus 4 plus a constant. Okay, and you can see that that's the solution here, but I want to show you why that is the case. Okay, it's valid for when you have any function that sits in the denominator and doesn't have an exponent, so it's not x plus 4 all squared or anything like that. Because you can rewrite this, all right, as the integral of x plus 4 to the exponent -1, right? So moving the function from the denominator into the numerator, right? That's just laws of exponents. So if we tried to use substitution to solve for this, just like we've done in the past, we could let u equal x plus 4. du by dx would simply be 1, because the derivative of x is 1. So if we solve here for du, we get du is equal to dx. Right, because then we multiply both sides by dx. So if we substitute that in, we get the integral of u to the -1 du. Following the power rule for that, we would get u to the -1 plus 1 divided by, again, that same exponent, -1 plus 1, plus a constant. Well, -1 plus 1 is 0, okay, so we get u to the 0 divided by 0 plus a constant. You can't have that. You can't have a function divided by 0. So you can see that every single time you end up with a function that looks like this, where it's just not the exponent squared, it's just x plus 4, or even something like, x squared plus 2, okay? That is not all in brackets to some exponent, like to the exponent 4. It's always going to come out as the ln function. Okay, that's going to be very important as we get into additional lessons in this unit. You're going to see why this integral is going to become more or less second nature to you later on in this unit, because you're going to start using it extensively to solve questions. So let's look at another example. You saw that we can't use the power rule, okay, when the item in the denominator here has an exponent, if you put it all in brackets, of 1. So you're going to see that's the same case here. But now you know that we can use the ln function. So we can look at using substitution as long as we know the integral we're going to take is going to be the ln. Okay? Knowing that that's going to be the case here, let's try doing it with substitution. So when you're looking at these, okay, and you know, or you have the inkling that it's going to be a ln, you always start with u being the function that's in the denominator. So I'm going to let u be equal to x cubed plus 3x. So in this case, du by dx is equal to 3x squared plus 3. So we look here and we know we're getting close. We have an x squared and a constant here. And we see here that we can factor out a term, a factor of 3. So this is the same as 3 times x squared plus 1, factoring out 3. So now we have an x squared plus 1 in both, okay? So, but we don't have a 3 there, so we have to remove this 3. So what we do is if we divide both sides by 3, we get 1 over 3 du by dx is equal to x squared plus 1. And now our last step, okay, is we want to also remove this dx. So multiplying both sides by dx, we get the dx's cancel here, and we have 1 over 3 times du is equal to x squared plus 1 dx. So substituting all of these values in, we get the integral of x squared plus 1 dx just becomes dx. So we're left with 1 over x cubed plus 3x is u times just dx. Okay, so I removed all of those terms. Now remember, I showed you in the last example why you can't use power rule. So now you know whenever you see 1 over a function, your integral always has to be ln. So this simply becomes, actually before I do that, I should tell you that I made a mistake. We should have substituted in 1 over 3 times du, not just du. Okay, so now you know that it has to be ln. I've already said that. First thing I want to do is take out the constant. Okay, so that's the same as 1/3 times the integral of 1 over u du. Now again, it has to be ln. So that means this must simply be 1 over 3 times the ln of the function u. Again, remember, absolute value, that's what those two bars mean, plus a constant. Okay, so you can use substitution. Just make sure when you substitute in this scenario here, okay, where you have u and it's to the exponent 1 in the denominator, that you don't try using the power rule. It's going to get you in trouble and you're going to start seeing the answer get closer to infinity. Okay, so let's look at our last example. It's the integral of 1 over 4 cosine of 2x divided by the sine of 2x dx. Okay, so again, you see a function in the denominator to the exponent of 1. Okay, it's assumed there. So when you see this, oftentimes you're going to notice that ln comes up as the integral. So starting with the function in the denominator, okay, I'm going to let u be sine of 2x. So the derivative of this, du by dx, is equal to cosine of 2x. And that's multiplied by the derivative of what's inside the function, which is 2, because the derivative of 2x is 2. So this means that du by dx is 2 times cosine of 2x. Now, solving, all right, for just cosine of 2x, I can do either option first. In this case, first, I'm going to move the dx. So multiply both sides by dx. On the left side, they'll cancel. So du is now 2 times cosine of 2x dx. So I only want to substitute in for this piece, meaning that I need to move this 2 to the other side. So dividing both sides by 2, we get 1 over 2 du is equal to cosine 2x dx. So substituting each of these in, what we get is the integral of, we have 1 over 4. So cosine 2x dx becomes 1/2 du, divided by what's now just the function u. So I'm going to move now the constant to the outside of the integral like I've done in the past. So 1 over 4 times 1 over 2 is 1 over 8. So we have 1 over 8 times the integral of now 1 over u du. So we come back to that same integral, 1 divided by u, and this is to the exponent 1, remember? So you can't use the power rule, but you can use ln. So this is the same as 1 over 8 times the ln of the absolute value of the function u plus a constant. So now simply substituting in the value for u, we get 1 over 8 times the ln of sine 2x plus a constant. Okay? Remember, this integral is going to be very important when we start talking about later functions, more specifically when we get into the method of partial fractions. Okay? So that's all I had for all of you in this lesson. Again, this is just showing everything by substitution versus the first video that I showed. A lot of this comes down to practice. So make sure that you try these practice problems and send me an email if you have any questions, okay? The more practice you do, the more you're going to be able to identify these functions quicker, okay? Thanks, everybody.